My absolute favorite fast food is In-N-Out, and my best friend, like most friends, sometimes gets on my nerves, and it seems quite a bit funny for me to throw a burger at his face. I, however, am very weak and need to find a way to maximize the face coverage and velocity, so it thwomps the best. That is, I need to make sure all of my energy is being directed into translational velocity rather than rotational velocity, so that Ke is equal to 1/2 mv squared is maximized, and Ke rotational is equal to 1/2 times I times w squared is as close to 0 as possible. And the way to ensure this for any body, if we ignore aerodynamics and assume the burger will stay as one body, the frictional forces inside will be overcome, and that is to equalize the moments or concentrate all of the forces around something called the center of mass. The center of mass is a really interesting way to simplify a problem. The idea basically goes like this. There's a place on any given body or point mass where the body acts like all of its mass is at this point, i.e. there's a point where all of the mass actually is. Now obviously this isn't exactly true. I could cut a slice of cheese and the slice still has mass, but it works in terms of the body and the forces around it. It acts like an average mass location, which is essentially how you calculate this. Now, the actual calculations of the center of mass revolves around something called a moment, and if you haven't come across cross products before, you should go ahead and study it, and its brother, the dot product. This is by no means a comprehensive tutorial on the cross products, but an intuitive way to understand it in this context. Cross products are a way to describe rotation with a convention to describe the direction of that rotation. So by eliminating the moments, we eliminate the rotation of the two masses if we support it by the center of mass. Moments, denoted by this capital M, are defined as M is equal to R cross F. We will first start with two mass system and then extrapolate from there. We get two masses, A and B, with mass MA and MB, and a location of XA and XB, with a center of mass as a location of XCOM. Now, these two masses counter-rotate, so it kind of acts like a seesaw, which doesn't rotate, it's perfectly balanced. That is, the moments are equal, so capital MA is equal to capital MB. Now if we substitute in our equations, and this is the radius of the center of mass, then we expand it, then move all XCOMs to one side, then simplify this and solve. This is a weighted average, and we can basically extend this to multiple planar particles, where Ri times Mi plus dot 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 divided by Mi plus dot 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 gives the location of the center of mass. Now you can imagine if we had more and more of these points, we get a closer approximation to an actual body planar line. Now, onto the math. We could get an infinitely close approximation of a plane of mass if we add an infinite amount of very infinitesimal masses, i.e. we add a lot of little things to make a very good guess at a big thing. How we do this is through an integral, an infinite adder. Let's say that we know how to bound this plane and we know how the mass changes over the plane, which is density. So we can integrate the density over the x-axis to add all of the x's once again. Notice the second graph has a very large number of dots, makes it look like a line. But we need 3 dimensions, so we need to add 2 more. To do this, we integrate our very thin line multiple times to form a plane. The same idea, the more lines is a closer approximation of a plane. Finally, the 3rd dimension, we integrate the plane to form a 3D cube in this case. This is just for mass order. The same process we used for the numerator can be applied to the denominator, and the final equation for XCOM is shown here. Notice the only thing we changed was multiplying the density and by its distance x. It is important to notice that XCOM is equal to x1 times m1 plus x2 times m2 plus x3 times m3 divided by m1 plus m2 plus m3 can be broken up into additions. So we can split it across addition, which suggests that integrals can do this too. For infinite points, we can actually split it into different kind of bodies. So we can find comps of composite bodies by using the comps of each individual body. So in order to calculate the com of burger, I can calculate the com of the bun, the lettuce, the meat, the cheese, the onion, using integration, and apply all of the force in line with his face and the com, and he will be smited by In-N-Out. Or you could just approximate it.